All right, let's look at this theorem. It's about the existence and the uniqueness of second-order linear equations. All right, let's say P, Q, and F are all continuous on an open interval I containing A. All right, initial value problem. All right, so initial value problem is a combination of differential equation and initial value conditions. And the differential equation is a y double prime plus p of x y prime plus q of x y is equal to f of x. Right? This is just a second order linear equation, and this one is non-homogeneous. And the initial value conditions are y of a is equal to b0 and y prime of a is equal to b1. All right, if that's the case, then this initial value problem always has a unique solution on this interval I. Right? So we're not going through the proof or anything, but let's look at an example. Right? Let's say you have this differential equation, y prime minus 2y prime plus y equals 0. This is a homogeneous equation. Right? So p of x is -2, which is a constant function, so it's continuous, and the q of x is in this case 1 and continuous, and f of x is 0, so they're all continuous because they are constant functions. All right, then initial value conditions are f of 0 equals 3 and f prime of 0 equals 1. All right, then somebody already found the two solutions of the differential equation, not necessarily satisfying the initial conditions. And the first one is y1, which is e to the x, which satisfy the differential equation perfectly. And another one, y2, which is x times e to the x, which satisfy the differential equation perfectly. But you can see that they do not satisfy the initial value condition. Right? If you plug in, for example, x equals 0, we are supposed to get 3. But if you plug in 0 here, you e to the 0, so y1 gives you 1. And y2 gives you 0. So it does not satisfy initial value conditions. So what we want to do is, since the theorem guarantees the existence and the uniqueness of the solution, maybe we can cook up a solution by taking the linear combination of those two given solutions. Right? So let's do that. All right, so I'm going to write the solution as y is equal to, right, we have an unknown constant c1 and times e to the x plus c2 x e to the x. All right, so since we have to satisfy this initial value condition here, right, I'm going to get, so I'm going to plug in x equals 0. So you have y of 0 is equal to, all right, e to the 0 is 1, so you're going to get c1, right? And plug in 0, it's actually 0, so it's just c1. We're supposed to get 3, right? All right, now we already know that here, c1 is supposed to be 3. Right? All right, so let's look at the derivative. So we have to find the derivative first. The y, sorry. All right, so let's find the y prime. All right, derivative is going to be c1, derivative of e to the x is still e to the x. All right, plus, all right, so c2 times, all right, derivative of x is 1, so 1 times the second, so you have an e to the x. And the plus, first guy is x, derivative of e to the x is still e to the x. All right, so we get that. All right, so let's plug in 0 and see what happens. So I'm going to do y prime of 0, so x equals 0. All right, so c1, which is 3, right? E to the 0 is 1, so it's a 3 times 1, it's 3. So plus c2, and if you plug in 0, you're going to get the e to the 0 is 1, and 0 times, so that's going to be 0, so plus 0. You don't have to write that, but you have that. And then you have the second initial value condition said it's supposed to be equal to 1. So I'm going to set this guy equal to, before that I'm going to simplify, it's just 3 plus C2. So this is supposed to be equal to 1. Right? Then we can just simply subtract 3 from both sides. You get the C2 equals -2. Right? So we found C2 value. Right? So remember that any linear combination of the two solutions is still going to be a solution of the differential equation. And on top of that, we made sure that we chose C1 and C2 appropriately so that it also satisfies the initial value conditions. Right? So therefore, we found the solution of the initial value problem. So y is equal to, and that's y is equal to, right? C1 is 3, so it's a 3 times e to the x. And C2 is -2, so -2x e to the x. All right, so this is the solution of the initial value problem, guaranteed by this theorem to exist and be unique. All right, that's it. I hope that this was clear.